Great. Maybe we go to the whiteboard now and look at that in a bit more detail. Don't need to look so worried, Will. Don't need to. We're just away from PowerPoint now, just a whiteboard. What could go wrong, right? So let's imagine a scenario. You've been brought in front of a customer who's got a particular program where they have a requirement for an operating system. Just given what we've talked about in Mosaic and how you've talked about some of the challenges around operating systems, how do you typically approach those kinds of environments and talking about how Mosaic can provide additional capabilities to that customer?
Yeah, okay. So when we get requirements for operating systems, which is the majority of requests we get, we want to make sure that we have the most differentiating beneficial properties we can in our proposal. And so we typically want to challenge the fundamentals of operating systems. We want people to understand that operating systems are fundamentally complex. We want to make sure people know that, especially when we're dealing with DoD, avionics, that there's so much that people take for granted when they're trying to build a software system. And so just at a fundamental level, we want people to know that there is a huge difference when it comes to how much code is necessary to support applications and what opportunities you have on making the system simpler when you embrace the Mosaic technology. I'll just draw out just basic start for orienting people on what the difference might be. Okay. All right, so I'm going to draw just two sides, and one side's going to be just kind of the general model on application relationships with operating systems and hardware, and application relationships with hardware with Mosaic. Okay. So I'll do some blue applications. Little guys here, and little guys over here. And we'll get some hardware at the bottom. This one we'll do quad cores. People like 4 cores. Only got 3 apps, I'll fix that. All right. So I'm going to here, fix that. So when we're working with operating systems, application developers don't want to know the details of hardware. All their assistance is really expressed as APIs underneath the application. So it's kind of up to the vendor to just, hey, we'll get your data in and out of this thing. We'll organize you with file systems. That's great. And people love that. And that's a good thing. But you don't know what's going on in there. And there's a lot of applications that are getting supported by lots of things, and you just don't really know how it's really implemented. There's this first thing that's just really obvious is there's just kind of this natural point of contention where you have to get your work done on the processor, you get data in and out through the processor, and you're always handing off control to some mystery item. And so you've got this, things all talking, they're all including these interfaces, they're all reading and writing to them, and the data somehow gets out here. And it takes some work to really understand, well, which core is really servicing these applications, how many segments of code are really being executed, how deep are these call trees, and these things are important, especially when you're doing safety work. All this stuff has to be accounted for. When you're doing security work, you're so concerned, hey, is this application going in places where this application has, are we, when you use things like access control policies at the top, do we know if they're, number one, the right policy? 2, can they be bypassed? Can one of these applications have higher privilege to the operating system? And all these just lead to lots of questions and lots of work to get your answers in places that you don't normally have access to. Even if you did it so complicated, it's just so hard. And so we want to at least give the opportunity where the relationship between applications and hardware doesn't actually have to be arbitrated by some opaque piece of work. So with Mosaic, we're using technology that's using hardware virtualization, where, to be fair, we know that applications still want standard APIs. So there's a box. There's still software that's going to do work on behalf of the application. But you have options. That box certainly doesn't have to be stretched across all of the applications. And what's also pretty interesting is sometimes these boxes can be really integrated with the application, where the application itself really has direct control over resources. And what this is really trying to tee up is this more of a model of distributed computing where all the processors and all their resources actually can be selected into subsets and given directly to applications where each application thinks it has its own computer. Why is that good? Well, these questions about which applications have access to your data, they go away when there's strong segmentation between the hardware elements. One also immediate benefit is certain configurations, which we recommend. You can also have applications that are just directly pumped into the hardware where there's no extra copies, no extra context switches between the application and the hardware. This really starts making massive improvements if you have really high performance requirements. And also if you want to be able to get very explicit information about the behavior of the system, down to at least the microsecond, maybe even lower at the nanosecond level. When you do things like context switches, there's just so much time that goes by. There's so much internal complexity where you just don't know whether or not some of the behavior you're looking at is really directly controlled by you or influenced by other environments. So if you really can start breaking apart the environments, that makes such an improvement in the ability to analyze these things. You can't break it apart without hardware virtualization. So that's something that's super important to understand is hardware virtualization is a technology that really allows software to start achieving greater levels of independence,
right?
Where software really can be packaged as its own independent workspace and just be loaded on cores where not all applications have to be using the same runtime components. They certainly don't have to have any overlap in resources, and that's just not something you get with operating systems off the chute, out of the box. They do force this homogeneous type of interface. And it's something that, yes, you can tweak, you can kind of get in there, but it takes lots of work. And so we also want to make sure there's user models to the Mosaic kind of model where it's kind of effortless, it's natural. If you really want things to be separate, you don't need to read a manual to go ahead and say, hey, run this command that will make sure that this process has got core affinity on this core. What if there's a different way to express that? And that's probably the next most important thing I want to talk about. All right, so we're talking about how do you set these systems up? Number one, is it different? Why is it better? What do you get out of it? And so one of the most differentiating aspects of Mosaic is the way you configure your system. Most operating systems have user models of configuration that are oriented around config files that are pushed into kernels, where this information is used as input for the kernel to create spaces, create policies for their timing behavior, things like that.
Right.
In our design, we do not do it that way. We do not want things that have a lot of complexity. We don't want things that have more control than they need. We also want things to be more structured and traceable. So we invented a architecture description language. It's akin to many types of system model design languages, but it gets very specific about the hardware description, and we create a model that allows you to bind actors to hardware and also overlay certain types of capabilities with access control policies integrated as well. How is this different? Well, biggest thing about it is that we compile this information. This information is something that could be standalone, a separate development environment. And you compile this information, what happens is the compiler will actually create images that are upfront loading your architecture on the processor. So instead of having a kernel that's trying to bootstrap itself to get to a point where it can read config files and then start construct, the way this works is your boot images just lay down the architecture. This actually does a lot of work when you're trying to deal with security projects and you want to limit the attack vectors, what type of peripherals have DMA access, what can intervene. When you are able to start putting structure up front, that helps so much. It makes you reduce the amount of work you have to do and say making high quality bootloaders, high quality drivers. If you can constrain some of these things where you can say, hey, this driver, it doesn't even load yet, or if it loads up front, it's already placed in a space that doesn't have access to other areas. I don't have to worry about that as far as a vulnerability. So So if we're looking at something like this, what this is trying to show, as I mentioned, this is like a space. We call these things rooms, these green boxes. And we have the CPU and it's kind of hardware down here.
Right.
And then we got your actors, your systems, which we'll just call this for now. The blue box, or the blue circles. And so what would that look like as far as setting this up? Compared to an operating system, you might just have a config file that shows like a list of all the applications you want to load. And you would just tell the operating system, hey, create some spaces for these things, load their binaries, and start executing in those spaces. But you did that pretty far down the road. In this approach, you had to have described it, right? So we have some configuration tools that allow you to describe your model the way you want it to behave. So all of your applications need to be assigned to spaces, which we call rooms, and these rooms need to have hardware, and all this stuff is accounted for. Right now it's in XML, it's written in XML. It's got a schema for it that's creating the semantics for how this whole model works. And so we've got some XML. We actually call that thing the HCV. Stands for
Easy for you to say.
Yeah. Human configuration vector, all right? And so this thing, which has the information that captures your model, gets plumbed into a compiler, and out that comes this binary. And the binary is that information that you use to load into the processor. So the binary goes in the CPU, and the first thing that you get is architecture, right? So instead of first thing you get is architecture. So these are constraints. That comes up first. What's so cool about this stuff, the HCV, is it's all traceable. It can be traced into your system requirements. You can also trace it down. One of the cool things we're working on right now for avionics is actually allowing you to trace down into the lowest levels of the interfaces to the CPU and being able to look at that and trace the things that you're using the CPU way underneath APIs to applications, down into hardware, and being able to account for those constraints back into your config file. It's just so much work, and being able to improve your ability to validate the claims that you're trying to make. So if you're saying, hey, these applications need to be partitioned, how does that work? If you just say, hey, I've got this operating system, and it does partitioning, and all you have to do is call these APIs, and I get partitioning, all right, well, I have to trust that you've done that. But if I can say, hey, I need partitioning, and you told me you need an express, and I can trace, and I can look in the hardware that enforces partitioning, and I can bring that back out and say, hey, these things are all correlating. That's great. That's actually tighter binding, and that's why your confidence in how you would validate that claim goes up.
Well, Will, it's an absolute pleasure. Great to meet you, and thanks very much for your time.